u-substitution. This is the rule you are going to use the most in calculus. If you are only taking the first semester AB calculus and not going on to second semester calculus, which is what BC is, this is going to be the last rule you need to learn for integration. You will have your integration techniques fully in at the end of this day. So here we go. I'm just going to show you u-substitution by taking you through it. It's partly backward chain rule, but it's more than that. And the more examples I can get through with you, the better off we'll be. So you are trying to look for a function that is inside another one, typically. As you look at this, you should notice x to the fourth plus 2 is inside the cosine function. And coincidentally, the derivative of x to the fourth with its constant multiple cut away from itself is multiplied there. Coincidentally. So these problems are set up to work. So the first thing I'm going to do is write down this choice of u. Once this choice is made, everything flows from that one choice. I need to find the derivative because I need a relationship between the differential dx and the differential du. U is just the choice variable that we're using. It's just a standard variable that we use. And so when I take the derivative, that derivative is du dx. And we get 4x to the third power. If we're trying to get a relationship between the differentials dx and du, then I'm going to multiply that dx over to the right side. Yeah, this is u-sub. It's a lot of fun. So you end up separating those differentials so that you can get a relationship between them. Now, if you see some slightly shorter ways to get to the next result, feel free to use them. What I'm going to do is I'm going to show you by way of, I need to know exactly what dx is equal to. So I'm going to isolate dx by dividing both sides by 4x cubed. So du divided by 4x cubed is equal to dx. I am now ready to substitute a u in where I chose to make a u. And once that u was chosen, I found a relationship between the differentials dx and du. I have to have a full conversion to u. Right now, I have this little x cubed sitting here to the side. I can't ignore it, but I have to see what happens. So as I go through a process of just flat out substituting in, I'm keeping the x cubed. I have cosine, but then I chose for the function inside cosine to be represented by variable u. Yes, a lot of times it's pretty much what's in a parentheses. And know that the biggest struggle people have at the beginning of u-substitution is trying to figure out what is the right u. So I substituted in the u. Now I have the dx, and I substitute into the dx, du divided by 4x cubed. And a miracle occurs. As if this problem was set up to make those x cubes cancel each other out. It's like the problem was made for u-substitution. All right. Once I simplify, I find that I have a constant multiple of 1/4. I can take that constant multiple of 1/4 and set it outside of that integral. I'm allowed to do that with constant multiples. And then I can see that I am now integrating cosine u with respect to u. And know that whatever variable that differential is using, that is the only variable that I can have inside that integral, at least while I'm in single variable calculus. So, what is the integral of cosine? Integral of cosine is sine. So I've got my constant multiple. The integral of cosine is positive sine u. It's an indefinite integral, so I need a plus c, but I'm not quite done. This integral began in terms of x, and I need to complete the problem in terms of x. That means I'm going to go back to the u-substitution choice and now put it back in. And there you go. That is how you can go through the process of u-substitution. Now, if you look back, kind of sit back and just look at it, can you see that this actually was a backward u-substitute, or I just used the same word, a backward chain rule? Can you see that it actually was a backward chain rule? And you might be able to see it if you think, hey, how about I now go forward? What is the derivative of the sine of this big giant baby? And I get the cosine of that big giant baby, give mama her baby, times the derivative of that baby. And when it comes to the derivative of that baby, when I include that 1/4 with it, because the derivative is 4x cubed, but then multiply that 1/4 and you've got x cubed. One thing that's beautiful about integrals is you can check your work when you're done by taking your result, find its derivative, and see if it matches the integrand. And I love that about solving differential equations. For those of you who are like me and check your work obsessively, it's a great way to check your work on the test and feel really confident if you got that integrand back. Okay, so here we go. Next example. And I'm just going to keep going through examples. I'm going to get through more if I don't pause and ask you like to figure stuff out, which is ideal educationally, but we only have an hour. So again, you're looking for a function inside of another one. So in this situation, we're going to try and see if 2x plus 1 works out. It works out if I'm able to get a full conversion, and that the conversion is something I can integrate. And I want to point out to you also, if you look at this, when I have an addition under a square root, that is a strong bond. 2x and 1 are a couple that cannot be broken. You cannot separate them underneath that square root. So we're going to work it out of the square root so we can break them up. Okay, so derivative. Du dx, the derivative of 2x plus 1 is 2. I'm going to multiply the dx over to the right side and divide the 2 over to the left side. And now I have circled what I chose to be u, so I can substitute that in. I put a box around the dx because that has to be substituted with, and let's see what we get. I have a constant multiple of 1/2, and then I have the square root of u du. And the square root of u is u to what power? 1/2. I have a full conversion. This is something I can integrate. So here I go. Add 1 to the exponent, and then divide by that new exponent or multiply by the reciprocal. I do have my constant multiple of 1/2 that I can't forget about. I have plus an unknown constant, and I need to go back to the original function. So these 2's will cancel each other out, and I will end up with 1/3 u to the 3/2 when the u is 2x plus 1. All right, we are 2 down. Next example, and these examples are in your textbook. So you can always look them up and read through the way your textbook goes through them as well. So moving on to the next one. I'm going to give you a tip about choosing u. Sometimes an entire denominator makes a good u. However, if you notice that your denominator has some exponent on it, which a square root is an exponent, you want to go for the u inside of that exponent in the denominator. This is a very, very common place to find your u's. So my u is going to be the 1 minus 4x to the 4th, or 4x squared, if I can read the numbers in front of my face. Once u is chosen, the process begins, and I just have to see if it works itself through. Du dx, the derivative, is negative 8x. I want to multiply the dx over to the right side and then isolate it by dividing negative 8x to the other side. And now I'm ready to put that substitution in and see how it goes. I have x in my numerator. In my denominator, I chose what I circled to be u, so I'm going to put that in. And then my dx is substituted with du divided by negative 8x. And magically, the x's cancel themselves out. Isn't it great when your x just goes away? Well, I don't know. Maybe that didn't fly past all of you. Okay, here we go. -8 in the denominator. That's just creating a constant multiple of -1/8. And I can always just suck that right out of the integral sign. 1 over root u can be written as u to the -1/2 power. And now this problem is set up ready for the power rule. Using the power rule, I add 1 to the exponent. And I either divide by that exponent or multiply by its reciprocal. I do have the constant multiple that I can't forget about. I've got to remember to put a plus c. And I've got to remember to go back and plug in the choice of u back in. So I end up with a -1/4. And I'm going to change this to a square root of u, where u is 1 minus 4x squared. Ta-da! Good fun, huh? All right. Sometimes the u substitution is very subtle. And people will look at this and sometimes miss that a u substitution is needed. So with e to the, I think it was 5x, the only way that you can just flat out use a formula without needing a u substitution is if your differentials variable is literally the only variable and it is directly in that function. If this had been the integral of e to the x dx, correct. If this had been the integral of e to the x dx, you would have just gone e to the x plus c and been on your way. But I have an exponent that is not just the variable. Sometimes your u substitution is just a constant times your variable, and that happens a lot. So much so that in the future, some of you are going to be quickly doing these u substitutions. In a couple of weeks or a month, I expect that a lot of you are going to look at this and be able to spit it out and write it down without even needing to show any work. For now, though, we're going to let u be equal to 5x. We take the derivative of u with respect to x, and that is 5. I multiply the dx over to the right, and I divide the 5 over with the du. And then I rewrite with the substitution. So this is the integral of e to the u, and dx is replaced with du divided by a constant. And that 5 is just a constant multiple of 1/5. And now I have the matchup of e to just the variable that is the same variable of the differential. And now I can do the integration using the formula. So 1/5 e to the u plus c, but I've got to go back to x. So we have 1/5 e to the 5x plus c. And after you do enough u-substitution, you start becoming very fast at it. But the first day that you do it, you're very unlikely to be fast at it the first day you do it. So give yourself time, do the process slowly, make sure that the process makes logical sense. You make a choice, you make a choice, and then that just snowballs and everything follows it. No other decisions are made. Now you're ready for something a little harder. And the hard part isn't choosing the u. As you look at this, do you see what a really good candidate for u is? It's usually something that's nicely just kind of sitting in another function. It's what I used to call the baby functions. I guess they're still babies. So I let u be equal to 1 plus x squared. That's just a terrible circle. Then I take the derivative of u with respect to x, and that is 2x. I'm going to multiply the dx to the right, divide the 2x to the other side, and I'm going to see what happens when I replace what I chose to be u with a u and substitute dx in. Yep, we do. So I have the square root of u times x to the 5th power times du divided by 2x. Now I get a little bit of cancellation, but not enough. And this divided by 2, I'm going to pull out as a constant multiple. And I'm just rewriting what's there. Now, we must have a full conversion. You have to have a full conversion over to u. If you cannot get everybody to convert, you cannot convert. You can't do it. So I said not too long ago that the only decision you make in a u-substitution is what is u going to be. That is your only choice. Everything is based on that. With me emphasizing that the way that I just did, you might see what I'm about to do. I must have a full conversion. I can make it. I can take this equation, I can isolate x. In this case, I think it would be quicker if I isolated just x squared, but I could go ahead and find the square root and plug it in. And x to the 4th power is the same thing as x squared squared. And I'm going to replace x squared with u minus 1. And then keep everything going the way it is. Now, at the very beginning, we had an addition inside a square root. You cannot separate that addition. That is a steadfast couple that will not break up. Through a u-substitution, you can manipulate the algebra to bring that addition subtraction into a place where it can be dealt with more easily. So I'm going to expand u minus 1 quantity squared, u squared minus 2u plus 1. I don't have a rule for multiplication, but I don't have an addition in my square root anymore. I can very nicely distribute the multiplication of that single-termed square root and get something that I can integrate. Woo! So remember, the key is always your choice in the u-substitution. I still have constant multiple 1/2. And square root of u is u to the 1/2 power. So when I multiply, I'm actually adding exponents. So 2 plus 1/2 gives me 5/2. 1 plus 1/2 gives me 3/2. And then plus u to the 1/2 power. And it is now ready for the power rule and all the rules that we have with integration. And I get the lovely add 1 to 5/2, multiply by the reciprocal, minus 2 times. Add 1 to 3/2, multiply by the reciprocal, plus add 1 to 1/2, multiply by the reciprocal. And then when you thought you'd had enough, we have to plug the u back in. And by the way, do you actually see a really nice simplification just waiting for us if we choose to use it? If I distribute that 1/2 through, it's going to just destroy all those 2's, which is nice. So now I end up with 1/7 times u is 1 plus x squared minus 2/5. U is 1 plus x squared to the 5/2 and 1/3. And this makes for a solution. I do want to let you know that sometimes this is simplified in the following way. If you look at the fact that each term has a 1 plus x squared to a power, you can factor that out if you take the smallest numerical power and have that be what you pull out. That means I'm going to factor out of that a 1 plus x squared to the 3/2 power. When I'm factoring, I'm dividing. When I divide all of this by this, what do I do to the exponents? I subtract them. That gives me 1 plus x squared to the 7/2 minus 3/2. And what is 7/2 minus 3/2? 4/2, which is just a nice integer 2. And then 5/2 minus 3/2 gives me 2/2, so 1. And then I have plus 1/3. From there, I could simplify this polynomial in the parentheses. But from this point, I feel like you can cope with all of that. And I need to move on to another problem. I just wanted to show you that the textbook will sometimes simplify in that manner. Okay, now, guess who we don't have an integral formula yet for? Yeah. We're about to have an integral formula for tangent x. And if you forget the formula, you can do the following to recreate it. Tangent is sine over cosine. I said a moment ago that sometimes a really good u is just plain the denominator. And that is this case. The derivative of cosine is sine. Now I can multiply the dx over to the other side, and let me show you what I like to do to write less. Oh my goodness, thank you. You're right. Negative sine x is the derivative. Yikesies. What I like to often do is take the function and the differential and just substitute it. It saves me the time of having to write sine x twice just to cancel it out, just to write the whole thing again. So sine x dx is replaced with negative du, and I'm going to pull the negative outside of the integral. And then I replace cosine with u. And what is the integral of 1 over u? Natural log of absolute value of u. But I need to put the u back in, and the u is cosine. Now, this formula is a legitimate formula that you can use. I personally prefer this formula because you can see exactly where it comes from when you look back at sine divided by cosine. A lot of textbooks, including yours, however, rewrite this using a log rule. And that log rule is if something is multiplying to my logarithm, it can become an exponent inside my logarithm. So if I take -1 and make it an exponent, now be careful, it is a literal exponent. It's not the inverse symbol, so I need to make sure I go parentheses exponent of -1. That is referring to reciprocal. And who is cosine's reciprocal? Secant. So know that you will often see this as the formula for tangent. But this formula works perfectly fine. Yes.
I'm kind of confused on how you went from having like du with negative sine x dx to creating an integral. Can you go over that?
Yeah. So what I'll do is I'll do the full substitution directly. So I'm going to erase what I have right here so that I can just redo that. So I'm going to go all the way back over to here where I have the derivative, and I'm going to multiply my dx to the right side, and then I'm going to divide du by negative sine x. So when I go to rewrite this integral, I have sine x divided by, I chose the denominator to be u, and the dx is du divided by negative sine x. And magically, those two cancel each other out. And I end up getting this negative sign times the integral of 1 over u du.
Okay, that makes perfect sense.
Excellent. So be aware of both formulas for tangent. Then usually in the classroom, I like to, at this point, give you guys time to try and come up with these three right here, the integrals of cotangent, secant, and cosecant on your own. And people are successful with cotangent. The other two are tricky, but I'm just going to keep riding on through because we are limited in time, more than the normal limited in time. So cotangent is cosine divided by sine. And just like before, I want the denominator to be my u. Then I'm going to find du d theta. And this time I get positive cosine. Then I'm going to multiply the d theta to the right, and I'm going to divide cosine theta over to the du side. Then this integral becomes, I've got the cosine theta in the numerator. I substitute what was chosen to be u with u, and I substitute d theta with what I found it to be in terms of du. Magically, goodbye to cosine, and I have the integral of 1 over u du. So when I integrate, I get the natural log of the absolute value of u plus c. U is sine x, or sine theta in this situation. And you have a formula. Textbooks like these formulas to come up as positive natural log of something. So for cotangent, the formula is usually left just like this. Now, for the next two, I'm just going to have to show you real quick why the formula that we get out of this works. You're going to need to memorize this formula, though. So I'm going to take that secant theta and I am going to multiply and divide by the same expression. And it's doubtful you're going to guess this, what expression works perfectly. That expression that works perfectly is secant theta plus tangent theta. And I repeat, you're going to end up having to memorize this. What I'm doing right now is not the process you're going to want to go through, but I want to show you that we get out of this what the formula is. If I make u the denominator, when I take the derivative, guess what I get? Derivative of secant is secant theta times tangent theta. Derivative of tangent is secant squared theta. And now distribute your multiplication. Bam! The numerator is the derivative. So I'm going to quickly say that this turns into the integral of 1 over u du, which integrates to the natural log of the absolute value of secant theta plus tangent theta. And this is the formula you're going to want to memorize. If you have to memorize that to get here, you have to multiply and divide a fraction by secant theta plus tangent theta, it's a bit faster to just memorize the formula. But I wanted you to see that it comes out of u-substitution. Just takes a little extra effort. Now, I'm not going to go through the process with cosecant. I usually like to do that in the class, and there are different versions that you can get for the integral of cosecant. Most of the time, people will, for cosecant, multiply the top and the bottom by cosecant plus cotangent. That winds up throwing in an extra negative, but it works. It is a formula that you can create if you like, but it's not the formula you're going to see in the textbooks. In the textbooks, they're going to multiply and divide the fraction by cosecant minus cotangent. And that happens to allow me to not get a times -1 outside. If you do cosecant plus cotangent, you're going to get negative natural log. This formula works just as much as the previous formula. Yes.
So could you also just make the integral equal to like the cosecant, for example? Could you just make it 1 over sine theta and then make mu equal to sine theta and then go from there?
Except that it won't work.
Why not?
If you go through it, you'll see that you run into a problem of you can't convert. And normally I like to spend time with that, but I'm looking at the time and, honestly, this class should be like a 2-hour long class, but it was reduced to an hour and a half, and now it is reduced to 1 hour. That makes this really difficult to get through everything. So unfortunately, I don't have time to get through that and give you a quiz and show you how to do this. So, oh well. But I can talk about it later, given that we have time later. You can always come in during office hours and I can talk to you about it. Okay, I gotta go. Forward. This is a definite integral, and you need to know how to work with your definite integrals. You can start the u-substitution normally. So I'm going to choose a u of 2x plus 1. The derivative of u with respect to x is 2. I multiply dx to the right, and I divide 2 over to the left. Then this becomes the square root of u times du divided by 2. But you cannot put the numbers 0 and 4 on this integral. Whatever variable the differential holds, it is understood that that is what those numbers are representative of. These are representatives of x. If I put them in my lower and upper limits of this integral in terms of u, I will have written this very incorrectly. But there is a way to manage this. And that is, you have a formula. This is the key to everything. When x is equal to 0, plug it in. What is the value of u when the value of x is 0? I get 1. I always put that in the same spot as the number that I plugged in to find it. And there's a whole thing about a directional issue that I don't know, unfortunately, have time to get into. Just know that you keep it as a lower limit if it came from a lower limit. Then, if I substitute into the x this 4, what does that make u become? 9. Now, if you convert the limits of the integral over to u's, do not go back to, drumroll, your x. Ha ha, ha ha. Don't go back to your x. Okay, yeah, maybe that joke didn't hit you. Okay, so definite integrals are numbers. These two give the same exact number. So when you have a definite integral, if you change its lower and upper limits, you do not go back to the previous variable. And know that the AP test has a way of asking you questions where you have to know who this integral is equivalent to. And in a multiple choice setting, you better believe they're going to write this integral with a 0 and a 4 to try and trick you. So, yeah. Solving this integral, I have this 1/2, and then when I integrate the square root of u, I'm using the power rule on u to the 1/2. I add 1 to the 1/2 to get 3/2, and then I multiply by the reciprocal. I can put a plus c, but I'm not going to waste my time because it's a definite integral and it's going to subtract itself out. Then I end up getting 1/3 times, and I'm sorry I'm going through this quickly, but I've got to. When I plug 9 into the u, I first take its square root, and then I cube it. So square root of 9 gives me 3. 3 cubed gives me 27. When I plug in 1, I get 1. And I wind up with the fraction 26/3 is my answer. Yay! Now, we've got like 9 minutes before lunch starts. I would have liked to have gone through another example with you on doing this, but you probably need the time for your quiz. Know that you can look at this example in your textbook if you need more examples. then tomorrow